Welcome to mathematical induction, where we're going to prove divisibility results. So we looked at mathematical induction in the last video, and we proved that certain types of statements can be proven using mathematical induction. So today we're going to look at divisibility, or you can also do it as multiples. It's the same concept. So the steps are: we prove true for n equals 1 or the lowest value of n. So that's either n might be greater than or equal to 0, in which case you'd prove it for 0. It might not work until n is greater than or equal to 3. So you'd start at 3. Step 2 is assume true for n equals k. And for this step, though, we are going to make it a multiple of some integer m. And then we use this for substitution in step 3, like we did in the last video. Step 3 is you prove true for n equals k plus 1. And the final step is you just say, hence, by process of mathematical induction, we have proven that this is divisible by whatever it happens to be. So first one is we're proving that 7 to the n plus 3 to the n is divisible by 10 for all odd integers. Notice that it's odd integers, so we'll talk about that in a sec. So for n equals 1, so 7 to the 1 plus 3 to the 1 is 10, and that's divisible by 10, so it's true for n equals 1. Assume it's true for n equals k, so we replace the n with k, and we get 7 to the k plus 3 to the k equals 10 lots of m, because it's divisible by 10, so we're saying 10 lots of m, where m is an integer, so a whole number. At this point, suggest you rearrange the left-hand side to make one of the terms the subject. So I've just chosen 7 to the k, makes no difference. It's just that we're going to use this as a substitution later. For all odd integers, so that means that if n equals k, the next one we're proving for is n equals k plus 2. So we get 7 to the k plus 2 plus 3 to the k plus 2, and we're going to prove that that is divisible by 10. So we're just going to take out, so that we get that 7 to the k that we're going to use from step 2 to substitute. We know that 7 to the k plus 2, we can split that and make that 7 squared times 7 to the k, because just as you can add your indices if your bases are the same, you can also split them. And the second one becomes 3 to the 2 times 3 to the k. And therefore we get 49 lots of 7 to the k plus 9 lots of 3 to the k, and we're going to replace that 7 to the k with that 10m minus 3 to the k. So expanding your brackets, you get 49 lots of 10, which is 490. Be careful not to multiply. That's 49 lots of 3 to the k. It's not 49 lots of 3 and then make it to the k. It's 49 times 3 to the k, and then we're going to add the 9 times 3 to the k. Minus 49 plus 9 is minus 40. Take the 10 out, and it's divisible by 10. So it's true for n equals k plus 2. Hence, by the process of mathematical induction, we've proven that 7 to the n plus 3 to the n is divisible by 10 for all odd integers. What about doing it for 7 to the 2n minus 1 plus 5 is divisible by 12 for n greater than or equal to 1? So this is out of the 2007 paper. Once again, step 1, n equals 1. So we get 7 to the 2 times 1 minus 1 plus 5. That is equal to 12. So that's divisible by 12. So it's true for n equals 1. Do it for n equals k. So we get 7 to the 2k minus 1 plus 5 equals 12m for some integer m. So it's 12 lots of some integer. Rearrange the left-hand side. So the easiest one is to just leave the 7 to the 2k minus 1. So step 3, we're proving true for n equals k plus 1. So we substitute the k plus 1 in, and we get 7 to the 2k plus 2 minus 1. Now we're going to need that 7 to the 2k minus 1 because that's our substitution. So we'll take out the front 7 squared and then do our substitution. So using the substitution, so we're going to replace that 7 to the 2k minus 1 with 12m minus 5. Expand your brackets and you get 588m minus 245 plus the 5 on the end, and 12 goes into that, so it's divisible by 12, so it's true for n equals k plus 1. So therefore, using mathematical induction, we have proven that it's divisible by 12 for integers n greater than or equal to 1. Thank you.